Hello and welcome to Book Bites, a book club podcast for developers. And this week we're talking about two more chapters of the Imposter's Handbook, a CS primer for self-taught programmers by Rob Connery. And this week we're going to finish up the chapter on data structures and then talk about simple algorithms. I'm Adam Garrett Harris.
I'm Jen Luger.
I'm Safia
I'm Jason
Abdallah.
State. Go, Safia.
I'm Safia Abdallah.
I'm Jason Staten.
All right. Do we want to do another book news? Because I've got one.
Let's hear it.
All right. Eloquent JavaScript. The third edition is coming out. I don't know if y'all are familiar with it, but it's the yellow book on JavaScript with a bird on it, like a peacock.
Yeah.
So it's going to be updated with all the new JavaScript stuff, and it's always been free, and you can already read it online for free. And then a paper edition is going to come out in October. So that's pretty exciting.
Nice. I'll have to check it out.
All right, so we need to finish up data structures real quick. What is a hash table?
I'm like flipping pages. Where's the hash table page?
115.
Oh, you mean the one that I have marked as start?
So hash tables are a data structure that goes and indexes the values within it by going and hashing those values into a computed value that is consistent for all the values put into it. And because everything is based upon its hash, going and adding to and looking up items from a hash table are usually a big O of 1. They're pretty consistent, so long as your hashing algorithm can produce unique results for the values that are passed into it.
Yeah. So I think it's pretty interesting what happens when there's a collision. One option is you just like move to the next available spot, but that could get really bad. Or you could just use a linked list if there's more than one value there.
Yeah, that's definitely a challenging problem to deal with. And hopefully you write a decent hashing algorithm so you don't have to bump into that very much, because I'm sure perf goes way down as you wind up having lots and lots of collisions.
Yeah, I remember in college we had to try to write a hashing algorithm that didn't have very many collisions, and it was extremely hard. But I guess generally you're not going to write your own.
Yeah, a lot of times libraries that you use will have, whatever language you're using will have a hash table built into it. Especially if you're using something like Ruby, where hash tables are like the core data structure that you use everywhere. And so they've actually had times in the past where they've made pretty dramatic improvements to it, and it just speeds up Ruby across the board because they've made hashing faster.
Cool. Well, unless anyone has something else about hash tables, I think we're going to skip over dictionaries and talk about trees.
Trees.
What's a tree, Jen?
Trees are a type of graph. Essentially, it's pretty much what you're used to seeing regarding data. They have like the bubble at the top, and then they have the bubbles that are divided from down below. A tree, kind of like a family history tree, where you have you, and then it breaks out, and you have your parents, and then you have each of them has their parents, you've got great grandparents, all the way down. So that's technically a binary tree. But trees don't necessarily have to have just two values on each side. They could actually have a really large set of limbs as you follow that tree.
Yeah, a family tree is kind of interesting, right? Because you've got, I guess it's kind of upside down. Or you would have to start with yourself. You'd have to start with yourself at the top of the tree.
Yes. And
And then your parents below you, and then their parents below each of them. Okay. I was thinking of it the other way around. Like if your parents are above you, it's definitely a graph, but that would be, I guess it's also a tree.
it's technically a heap, I guess.
Yeah. Yeah, based on age.
Yeah. Birth date.
So you said it's a type of graph.
Yeah, that's actually a note that's mentioned later on in this chapter, towards the end, when they actually do cover graphs. And they say that all of these other data structures that we've covered throughout the chapter are all also forms of graphs. It's kind of mind-blowing.
Yeah, so I think the key difference between a tree and a graph is that a tree is a graph that is acyclical. So it has no cycles. So there's never a loop.
Yeah, it's a hierarchical structure, which is linear.
Yeah.
I always found them funny that they called them trees, primarily because when you're used to looking at trees, you're starting from the trunk and it goes up into the sky. But almost all definitions of digital trees are the trunk is in the air and then everything goes back down, kind of like roots instead of branches and leaves. Alas.
Yeah. I think of it as it's kind of like a Christmas tree where you start at the star.
That's a good way to
Same
put
here.
it. But I never made that connection.
And then you're going from ornament to ornament on the way down.
Well, that's deep.
Yeah.
I hadn't thought about it as ornaments, but I did definitely have the Christmas tree vision in my mind. You just draw a little straight trunk underneath of it and put some presents there, and you're good. So a common place for trees that I can think of that I myself have actually interacted with, actually pretty recently this week, I had to write a code mod for some JavaScript at work where we needed to go and upgrade a jQuery version from 2 to 3. And there are some common cases where if you find a certain pattern, you need to go and swap it out with something else. That's kind of what a code mod allows you to do. And when you are creating a code mod, you do it based on what's known as the abstract syntax tree, which is a tree data structure that is created from reading and parsing JavaScript code. So you wind up having a tree-like structure that perhaps is a function expression, and a function expression has a couple of children underneath of it, one of them being a parameters type node and also a body type node. And then the body type node has member expressions where it's maybe calling console log or something, and it goes real deep. But there's a really cool tool called AST Explorer that you can go and put a snippet of JavaScript code into, and it will give you back the tree structure that represents that piece of code. And it is invaluable for creating code mods with.
Or anything that you're trying to transpile,
Definitely.
like Babel.
Yeah, I guess also with TypeScript or linters.
Mm-hmm. Speaking of which, I just released a linter last week.
You released a linter.
I did.
What?
So you know how we have ESLint plugin JSX A11Y?
No.
Yes.
You didn't know?
No.
So there, ESLint though, right?
Yeah.
Well, ESLint plugin JSX A11Y actually tests for accessibility while you're coding. So you can lint for accessibility requirements.
Awesome.
Yes. Well, it turns out that when we're talking about React Native, it kind of lands right in that space in between the web and DOM and React, and the ability to test apps in the native world. So there's accessibility tests for the web through like Xcore or something to that effect, and there's accessibility testing through iOS and Android. But there's really nothing for React Native. So Formidable and a great guy named Alex Saunders wrote JSX plugin React Native A11Y, and I released it as part of my Chain React talk last week.
Oh, that's awesome. Congrats.
Thank
Nice.
you.
That's
Well-
I'm sure it's going to help a lot of people. And yeah, it's great.
Nice work, Jen.
Thanks.
So another type of tree is a trie. I think it's pretty funny because it comes from the word retrieval. So it technically should be pronounced tree as well, but then it would just be confusing. But, it's spelled TRIE.
I think it's not confusing already.
Yeah. It's pronounced try. It's not spelled that way anyway. And it's a tree. But it's a tree that can help you spell out words.
Isn't that cool?
Yeah.
It's like a word completion.
Yes. So it can be used for when you're typing into a search and you need to suggest what could come next. So as you go down the tree, it kind of narrows down what possible words you're typing.
Also, it's way
Nice.
cool that it shares parts of entries that are within that try as well. So,
Yeah.
for example, the word impart and imposters both share IMP, and so you actually don't wind up duplicating those nodes, but instead they are shared for each one of those entries. So tries are also space efficient as well.
Oh, yeah. I think another thing this picture in the book doesn't show is where a word ends. So, for example, imposters could actually end at imposter. So I think one thing you can do is at the end of a word also add a node that's just like some sort of indication, like a null node or something, some sort of indication that can be the end of a word.
Yeah, I can see the need for that if you had a word that is completely within another word.
Yeah, like you can't assume that impost is a word, but impostor is.
Yeah, but I'm not entirely sure that you need to define the end of the word because the word itself ends. So imposters may fall completely within that word, but you're going to end up with imposter and imposters under the imposter parent.
Yeah, but it's
So-
just hard to tell. Is imposte? Is impost? Is impos? Impo?
But as you go down that list, it's going to limit based on what's available.
Yeah, but if someone typed an IMP, you wouldn't want to suggest impo as a possible word. Unless it's a really word.
But no, there wouldn't be anything under impo
But how do you know you can suggest impostor and not imposters?
because imposter exists and impo doesn't.
But how do you know it exists?
Because it's one of the children.
Impo exists. IMPO.
I think you probably could do some sort of like suffix check. So like imposter and imposters are two words and they both have the same like imposter root, or I guess impost, depending on how you look at it. But like, what is the root of the word impo? Like there's no valid root for it. So it might be that, or maybe like each path on the tree is ranked. So, it's more likely that from O you want to go out to another node than terminate at O.
I mean, if you're looking at that picture, what you're looking at is that you have imp and then you have it break out into impart, and it separates into the O, but it completes it with osters. So you'd have osters, or it would go all the way down to oster, and then you'd have a side node that would have an S. So it would become a sibling to the R. You end up dividing it, but because of the fact that impo isn't a child under the O letter there, it's not one of the options.
Okay, so I'm looking at actually a different book I used when reading this book. There's another book I use as a reference, and it's called Cracking the Coding Interview. And so when it goes over tries, it says it has little note. Yeah, it says there's null nodes to indicate complete words, and it marks them on the graph with an asterisk. So, for instance, it's got man and many. And so after in, you have a Y and an asterisk. And then after Y, you have an asterisk. So, yeah, I feel like that's just something this book kind of glossed over. Because it's just not going into that much detail.
This discussion definitely makes me want to go and implement it just to see what approach I would have to take to make sure I'm showing only entries that are there and not every partial entry. So I could take that on for you, Jen, to see what I can find from that side of things as a little challenge to myself.
Sure. It'd be interesting. I mean, I've used auto-completions. I've written auto-completions, but...
Yeah, and I may not have entirely understood what you were trying to explain with just audio only.
Yeah. It's just anything that came off of O would have its own... It would be like all the children that came off of O, but because there's none that just ended O, I guess. But that would be part of your definition, is that there's no asterisk all by itself as a child saying impo is a possible word.
Yeah. All right. Should we move on to algorithms?
Yeah.
So actually, we've got a sponsor first.
Do we?
What?
Yeah. So this week's sponsor is vSchool. vSchool was established in 2013 and is Utah's highest ranked coding bootcamp. And it's the first of its kind in Utah. You can choose to learn full-time or part-time in the evenings, and you'll immerse yourself learning new skills. So even before classes start, you'll get a career counselor to help you find a job when you graduate. And they take care of everything so you can focus on learning, including free housing if you need it. And the housing is just a few blocks from school. It's located in beautiful Salt Lake City, Utah. Or you can learn from the comfort of your own home with vSchool's 100% virtual classroom. You'll get a super transcript, which is kind of like a portfolio, transcript, and letter of recommendation all in one. And it will help a potential employer quickly understand your strengths and abilities and what you've accomplished.
That sounds pretty cool.
Yeah. If you're interested in vSchool, head on over to vschool.io and it will help support the show. And definitely tell them that you heard about it from Book Bites. Thanks to V-School for supporting the show. So, simple algorithms. So Jason and I were talking about this, and our algorithm for going through these chapters was O of N. Well, actually, MN, where M is the number of hosts and N is the length of the chapter. And so we wanted to speed that up by each of us just picking our favorite algorithm. And so that should make it O of 1.
You nerds.
I definitely agree with that. So
The nerd part or the O of 1 part? Because
I'm not going to backtrack from either. I've definitely been geeking out with this book. I really enjoyed it so far.
Yeah, it's been great.
So speaking of geeking out on things then, I actually will jump in line and I will talk about my sort that I wanted to do. So first, kind of going back to the last chapter related to a data structure that we didn't spend a lot of time on, but it is a tree and it's called a heap. And a heap is a special kind of tree where a parent either has a higher or lower, they call it priority, but like you can think of it as a value, than its sibling nodes. But those sibling nodes themselves don't have to have any specific order to them. So for example, if you were to have a heap of 3 nodes with the highest priority up the top, say you had 3, 5, and 7 as your values within it, then 7 could be at the top, and then 5 could be on the left side of that, and 3 could be on the right side. The order of 3 and 5 doesn't particularly matter. And the value in that is that you can insert and move things around within a tree pretty quickly, because as we talked before, a tree winds up becoming a divide and conquer type strategy when you're interacting with it, where you only need to figure out which level something belongs in rather than having to figure out the exact position of something within a tree when you're inserting or removing and rearranging the tree. So first, a heap has the value or use case of being useful for a prioritized queue, and a prioritized queue would be something you would want to use in the case of, say, you have a RabbitMQ type worker process where you have a queue of things that you're putting a whole bunch of tasks into, and sometimes tasks will have higher priorities than others. By using a heap, you can insert into them very quickly with it is a log n type insertion time to put something into that, and then actually pulling off of the top of one winds up being a big O of 1 operation to go and remove the item because it's exact where it's at, and then a log n type operation to go and rebalance the tree again. But heaps also have the benefit of being useful for sorting as well. And the way that you can do that is by converting your list structure, oftentimes it's an array, and reorganizing the items into a complete heap structure. And a complete heap is one that happens to have the greatest or lowest priority at the root node or the first node on it. And then your second level of the tree and third level of the tree are just denoted purely by the indexes within that array. So kind of a cool thing about it is a heap can be represented by a array type structure, and you don't actually have to have individual node type structures that point to other structures. So it makes it really memory efficient because it's just a contiguous set of memory. And because of that, going and doing a heap sort winds up being an n log n type big O. And I just thought it was pretty awesome. I went and actually implemented it today in Rust, and it is by far the fastest algorithm that I went ahead and implemented. I did bubble sort, insertion, merge, selection, and heap. And heap, I mean, because of its n log n type speed, it outdid everything that I wrote, but the built-in sorts are still definitely faster in terms of actual runtime. Their big O's are still the same as heaps being n log n, but heap is definitely on top, or it's top of the heap of my sorts that I wrote.
Nice.
Yeah.
So, question.
Yeah.
So normally a heap, like you said, a min heap or a max heap would be represented with a tree, and it looks like a tree. Like when I see a picture of it in the book here, and you said you can actually do it as an array where you just specify what level of the tree each item would be at if it were in a tree. And that's great because it's contiguous piece of memory. Do you do that for a sort because you already know how many items are going to be in the heap? And like normally, if you were just building the tree ad hoc, you would know how many items are in there?
So even if you are building it with an unknown or set of entries in it, that is a case where it could be backed by one of the more dynamic type list structures, like the dynamically allocating arrays, that when they get beyond their capacity, they go and reallocate another set of memory, kind of like what JavaScript arrays do automatically for you. And some other languages like Java has a list that will do that under the hood. So it's not so much about knowing the size, but the benefit can come from, first, if you are able to back it with an array, a lot of times arrays are the type of thing that you want to be sorting. I mean, I generally don't find myself sorting other types of data structures too often. And so by using a heap sort on it and just backing it by the original data source, then you actually don't have to go and allocate other memory in order to do the sort. Whereas some other sorts actually require you to go and copy the original data source in order to rearrange it. So it's in place and doesn't require additional memory allocation, which is good for like low memory type devices and stuff. And the way that you can go and specify what level something is at is by looking at its index within the backing array. So for example, index of 0 is the root node, and there's only one node at the root node level. And then indexes 1 and 2 are nodes that are at the second level. And then indexes, I guess, 3 through... Oh, you got me multiplying now. Yeah, so like everything under there, so you have 4 nodes under there because every layer is 2 to the whatever level that it's at, and it's just known by the index that it's at. So you're not even like keeping track of this is the level that thing's at, other than relying on the existing index that it is in the array.
Gotcha.
And there is a really cool blog post about it, about heapify all the things, and it is written by Vaidehi Joshi on Medium, and I will go and share a link that you can check out there because it is an illustrated guide to doing a heap sort, and I found it as an excellent resource to go along with the book.
Awesome. Yeah, it seems like an illustrated guide would go great with the book. All right. Safi, you want to tell us about merge sort?
Sure. So I decided to choose merge sort because it was related to a sorting algorithm that I brought up in one of my tangents during the last podcast episode, which was timsort.
It's not a tangent. It's a side note.
It's a side note of, oh, that's right. We're being punny here. Perfect. One of my side notes during the last episode. So merge sort, although it's used in timsort, which we mentioned last episode, is actually a really old sorting algorithm. It was invented in the 1940s by somebody who was mentioned in the book a little earlier, von Neumann, who was tinkering a lot with computers in the 40s, as many of us do now, I guess. And it was really interesting about merge sort was it applied the principle of divide and conquer. And this is also something that the book touched on in the last chapter. And I think, in general, like divide and conquer for solving any kind of problem tends to be like a pretty common tool across computing. And merge sort was like one of the first applications of that. It's been around for 80 years and it's pretty reliable. So with all of that background aside, what does merge sort actually do? Merge sort essentially works by dividing the list that you want to sort into smaller and smaller sublists and sorting on those. So the idea is that instead of taking the time to solve or sort a list of 20 items, you sort the 10 lists of 2 items contained within that list, and then you build back up. And this actually ends up being a really efficient technique. We mentioned in the Big O chapter, we learned about how, generally when you have these sort of like divide and conquer type techniques, you get really good run times. And the run times usually tend to be log n because you're always taking half of what you were looking through before, generally. And that's the case with this. So the efficiency or the time complexity of the algorithm is O log n and log n. And Jason mentioned a little bit about how much space heap sort takes up. Merge sort takes up, I guess, a space complexity of ON, which basically means that if you have a list of 20 items and with merge sort you're breaking it up into smaller lists that you want to sort through, then you would need basically the same amount of space as the number of items in your list for all of those sublists that you're working through.
Is that in addition to the list you already have saved?
Yes.
Okay.
So ON extra space.
Okay.
Yeah, one of the things that I think is cool to note in one of the visualizations that is on page 145, if you're looking at the PDF, is you can kind of see how much merge sort looks like a binary tree because you've got those successive splits. And it was touched on in the last chapter, binary tree is basically a tree where every node is either a terminating node or has two children. So I thought that was a really cool way to showcase those analogous principles. Like, binary tree is a divide and conquer representation technique, I guess is the way you might say it, or data structure, and so is merge sort. That's all I have to say about it. My biggest thing was that it's like really old, as most things in computers are. It's been around for a while, and it's pretty time tested, and I think that's what's cool about algorithms. Once you've got something that's space efficient and time efficient, you can take it anywhere.
Nice.
One thing that confused me initially about merge sorts was, okay, we're breaking everything up, and now we have all of these lists of a single value, and then I'm merging them back together. Like, how does that make anything faster? Because then when I have a list of 2 and another list of 2, how do my initial thought was like, okay, well, I have to compare all of these things. And it turns out the efficiency comes from having those 2 lists of 2 that you're assembling back together. Those 2 lists are already sorted. And so the only things that you need to look at are the things on, I guess, the left side of the list or the head of those lists. And that is the order that you assemble them back. You don't have to check each item in one list against all of the items in the other ones. You only have to look at the heads of the list. And that's where the efficiency can come from.
Yeah, and the code, the JavaScript code on page 148 kind of shows that you're always just checking the first item. And the trend is kind of that, although you're still sorting, you're always sorting elements that are more sorted than they were before. So like your list is getting less chaotic as the algorithm runs, and you only have to compare those first things.
Yeah, Jason, I had the same thought as you. It seems and it doesn't seem very efficient because that's not how I would do it. I think he mentions in the book that the sort that's most like how a human would do it is selection sort, because you just kind of look for the smallest one and then look for the next smallest one.
Mm-hmm.
And I think that's, I'm going to go on a side note again. I will pause it. But yeah, it kind of goes back on, it was, because it was invented in the 40s, it was one of the first sorting algorithms that was designed to be written on a computer, and specifically like a von Neumann machine, because as is noted, you need the additional memory to keep track of all of the sublists. And then you also need like your CPU to actually do the magic. So it was like definitely like very designed to be run on a computer, and definitely not by a person, because I would not sort a deck of cards or something like this.
Yeah. Okay, so you said you need the additional memory. Jason, is the heap sort in place? Like, does it need an additional memory?
So heap sort does not need additional memory, so that is one benefit to it. It also did come a bit later. I think it came in the mid or later 60s, so definitely after merge sort. And one difference between the two algorithms as well, even though they have the same runtime, merge sort winds up being a stable sorting algorithm, whereas a heap sort is not stable, meaning that if, say, you have two duplicate items in terms of their priority or ordering, those may get swapped in a heap sort, whereas a merge sort will always make sure that if something came first before the list was sorted, like one duplicate came first before the list was sorted, that will continue to remain before it after the list is sorted.
Which doesn't sound important if all you're sorting is numbers, but if you're sorting numbers that have other data associated with it, it could be a big deal.
Yes.
Cool. Jen, what was your algorithm you wanted to talk about?
Mine is quicksort.
Sounds fast.
Yeah, well, sort of. So the thing with quicksort is it is an in-place sorting algorithm. It's also a divide and conquer sorting algorithm. So what you end up doing is you start with the very last element, and then you look before it, starting at the very beginning, and you determine if it's larger or smaller than the current or the very last element. So in this example, they had a list of numbers from 1 through 8. And they were very much jumbled up. So if the very last number is 6, then you're going to look at the first one, which is a 5. Okay, it's still bigger. Then you're going to look at the next one, which is a 2, and that's 6 is still bigger. And you're going to look at the next one, it's an 8. So what happens there is that you're actually going to swap those two numbers. So now you know that that end position is now like the largest of what's going on, right? At that point, oh, goodness gracious. Yeah, so you swap them. And then at that point, you're going to go drop down a number. So then you're going to look at the next one, and it's going to be a 6. Or the next one's like a 7. And you go back to the original position, and it's a 6. So they swap it all back around and things like that. So the point is that they're trying to take the end of the list and compare it to the beginning of the list and make sure that they end up in the correct order all the way through. So you end up merging in the center with the first half of the list and the second half of the list being sorted semi-separately. This makes it a n log of n type of algorithm, just like a merge sort. However, if the list is already sorted, it could be an n squared algorithm. So it can be much, much, much slower because it has to compare every parameter in the list on every other parameter in the list to verify that it's actually in the correct order. So to avoid that, you end up choosing a median number as your beginning pivot to verify that you know that the bottom half of the list is going to be different than the top half of the list. So that way you're only comparing half the list essentially at each time.
So it looks like you said you swapped the 8 and the 6.
Yeah.
It looks like you throw the 8
to the end of the list.
To the end,
right.
And the 6 stays as the second to last one. So it's actually the second to last one goes where the 8 was. So it's kind of like 3 different things moving around, but essentially you just throw in the 8 after the 6.
That's interesting.
I wonder, it mentions if you want to make it more efficient, then you pick a better pivot, which is a median.
Yeah, you choose a median.
So I wonder how you choose the median, because if you have it sorted already, that's easy to choose the median, but how do you know what the median is?
Probably the same way the rest of us do. We go through the list real fast and, find out the length of the...
Oh.
Right, because it's already n log n, and so for you to go and traverse the list one more time still keeps that same time. I mean, maybe it's 2n log n, but then we drop the 2.
It'd be n log n plus 1.
It would be n plus n log n, and then you ignore the n plus, because that's not that big of a deal.
Right.
So I guess what you do is go through the whole thing and, I'm trying to construct an algorithm just off the top of my head. But basically, like, you'd have a list of smaller numbers, a list of bigger numbers, and then you have a current median, and then you might find one that's more median than that.
Mm-hmm.
Because a median is more than just like, it's mean is where you add them all up and divide by the length.
Yeah, median is the middle number.
Yeah.
So you find the length of it, and you just divide it in 2 and grab that one. So it's almost just an index sort. It's just a 1.
Yeah.
I know that a quicksort is actually what Rust chooses to use as its default implementation algorithm. And I don't know what strategy they use for making sure it doesn't run into the n squared type situation, but they have a, I think, white paper that they link to in their docs that I'll have to go and pull up. But yeah, there has been a lot of thought into that, because you definitely don't want to run into the worst case, or in that point, you're better off potentially choosing some of these other algorithms. Like if you're likely to run into a sorted data set, which sorted data sets are things that we run into a lot, which is why, as we brought up last episode talking about TimSort, where it can go and kind of gather heuristics about those things. And if it's looking like it's sorted, then just roll with it and assume that.
And I wonder if it's actually a combination of a merge sort and a quick sort. So if you go find your median, then you've got your one list of numbers on one side and your other list of numbers on the other side. And then you're at least using your pivots at that point to make sure that each half is sorted. And then all you're doing is picking the first number of the first list and the first number of the second list and going, yeah, they're good. So they end up being really, really similar. The reason that a quick sort is considered a quick sort over a merge sort is because there's fewer pivots that actually have to take place compared to the number of steps that are in a merge sort, usually. So it tends to be faster.
Gotcha.
But not always.
All right, I want to talk about graph traversal. I think mostly what it's talking about in this book is traversing over a tree. That's like a pretty common type of graph traversal. The difference between traversing over a graph that has cycles or loops and a tree is that if it's a graph and has cycles, you have to mark each node as visited. So you make sure you don't get into an infinite loop and keep visiting the same nodes over and over.
I feel like this is just such a difficult chapter to go through because it's so visual. And all we have is audio at this point. So it's hard.
Yeah. So, and then when it comes to traversing over a graph, you have two possible ways to do it. One is depth first and one is breadth first. And so depth first just keeps going down as far as it can until it can't go any further. Then it goes back up and goes down as far as it can and back up. And that might be what you want. And that method uses recursion. And if you want to use breadth first, you might think that uses recursion too, but you can't really, I don't think it's possible to do that with recursion. Instead, you use a queue. Now, what I learned from this book that I didn't know is that you can use a stack to do depth first, and then a queue, of course, to do breadth first. It's pretty interesting. So, like, you just add the top node, the root node, to the queue or stack, and then as long as there's something in the queue or stack, you just keep adding its children to the queue or stack, and then you just keep looping, and you pop off the next thing. You just pop off the next thing and add its children to the queue. So one of the reasons why you might want to use breadth first is you might want it to stay as close to the root as possible and not get too far off track. And one of the reasons you might want to do that is you're trying to find a path between two nodes. And so if you do breadth first, you may only have to go 4 levels deep to find it. Whereas going depth first, you might have to search through the whole tree almost, because you don't know how deep the tree is going to be. And what's also super interesting is if you want to find the path between two nodes, you can do simultaneous breadth first searches from both of those nodes. And then as soon as they overlap, you've got a path. And that was not in this book. That was actually from Cracking the Coding Interview.
That's an interesting point. You did bring up traversal of just any graph, and there is actually a way, or like a pretty common way, to go and find if there is a cycle within that graph. And there is an algorithm called Tarjan's Strongly Connected Components Algorithm. I'll send over a link to the Wikipedia, but its time in order to do that is a big O of the number of edges and nodes that are within the graph. And by doing that, it's able to go and determine if there is a cycle within that. And kind of like you said, it's going through and keeping track of nodes that have already existed simply by building up a stack. And so it actually has to be done in a depth first sort of manner, because if you do breadth first, then you don't have necessarily the history of where you've been everywhere else. And if you're on a cycle, then you will continue to stay on that cycle indefinitely, potentially.
Oh, yeah.
So it is certainly an interesting algorithm, and I'll link to it.
Yeah, and I bet it's cool to see videos of a lot of these things because you can see the path as it changes and goes up and down the tree.
Yeah, the Wikipedia article has a little animated GIF that it actually calls out all of the cycles that are within a little sample graph, so you can actually see which cycles exist, not just does one exist, but where are the cycles actually at.
Oh, nice.
Yeah.
All right, we actually made it through that chapter in a decent amount of time.
We did. I'm surprised.
Yay! All right. So thanks so much for listening. If you want to support the show, please go rate us in iTunes. You can follow us on Twitter at BookBitesFM. And I'm at Agarhar. Safia, what are you? You're at Captain Safia,
Yes, I am.
right? Jason, you're at Staten Jason.
Correct.
And Jen, you're at Knit Code Monkey.
Yes, I am.
Awesome. So who wants to read a review this week?
All right, so Masonite.bmw said, I have listened to one episode and loved it. I look forward to reading a few of the books they tackle. It's good to hear the insights from other people. When I read stuff on my own, sometimes I only see it through my own perspective. This podcast adds a lot to the experience of reading books around the tech industry. Thank you, Masonite.bmw.
Yeah, and Mason is actually a friend of Jason and I both know him. We've worked with him, so I appreciate that.
Well, thanks.
Yeah. All right. Next episode is advanced algorithms, and probably that's it.
I could see it taking up a good chunk of time, but also I did definitely like the strategy this time of going through and each of us kind of digging into one specific one. I liked it.
Yeah, I think we can do the same thing next time.
Sure.
All right. See you next time.
Bye.
Bye.
Bye.